Or not.
We don't have a microphone, so welcome everybody and give it up for Gary.
Hi, Mark.
A smart man that knows a lot of things about a lot of things. I'm very happy to have him here.
You lucky people. The premiere of this talk. I literally finished it 3 weeks ago, before we got on this ship. The 29th of January, it was finished just before that. All right, we have to move quickly because the captain's announcement is going to come on at 9:45 sharp, and I want to be finished. Today's humorous offering. Read it. Thank you. Thank you very much for that. Right, let's move on. Who discovered the first dinosaur bone? We don't know. People have been discovering these things all through history. A couple of pictures give you an idea of maybe what they found. And from those discoveries, from things that they didn't understand, we have invented mythological creatures, like this one. And I chose this one for a very specific reason, which you may or may not know. Yes, this is Smaug from Lord of the Rings. This is a dragon. And because of these large bones people found, they invented all kinds of mythical creatures. This one being one of the more famous mythical creatures that has been developed through finding these fossils. All right, as wonderful as that is, let's move on because that's not a dinosaur. All right, what's the first one? 1677, we find a picture shown up there on the right in a document that is a fossil. Didn't know what it was at the time. He actually thought it was part of a giant. About a century later, it was identified as a scrotum humanum, which is also incorrect because it is in fact part of a megalosaurus. But they didn't know that yet. They didn't know what it was. And so, what happened? The next steps in developing our understanding of dinosaur took place as early as 1847, because Mary Anna there discovered whole skeletons in England, ichthyosaurus skeletons. I'll show you an ichthyosaur fossil skeleton a little bit later. But the other thing that happened before her discoveries was in 1815, which is called George Cuvier. We started to develop comparative anatomy. So we look at the anatomy of things we understand and we compare that anatomy to things we don't understand, and it gives us understanding of the things we didn't understand because we understood something in the first place. So in other words, if a bone looks like a leg bone on one animal and you've got something that you're not sure what it's from, but it looks like a leg bone, then the chances are we've discovered a leg bone of another animal. Do you follow? Good. Excellent. Lovely. Now in 1824, Buckland named this creature. Here is a drawing of what they found. This is a fossil. It is the jaw of a megalosaurus. He named the first dinosaur. They didn't know it was a dinosaur, but nonetheless they gave it this name, Megalosaurus. And in fact, here's a print of him teaching at Oxford University, talking about the things that he has found. He was a geologist, actually. And you see on the floor there, various little pieces of fossil down here. And he's talking about those. And there's an ichthyosaurus head, actually, fossil head. Behind him was an ammonite. This is what they thought it looked like. This is in London, in Crystal Palace. You may have heard of Crystal Palace. It no longer exists. It burned down. It was a big exhibition centre. And they thought it was a giant lizard creature. And that was their idea of what Megalosaurus looked like. Well, we understand it to look a bit different today. Over on the right, we see what they thought it looked like. And over on the left is what we think it looked like now, from understanding what we do understand of dinosaurs and all of the other things that we have developed. And I'll talk about that towards the end, how we know what we know. This is how Megalosaurus changed through time. As our understanding of dinosaurs evolved, as we learned more things and we were able to do more experiments, some theoretical and some practical, to figure out. So we go now from a four-legged creature to a two-legged creature, looking a bit like an iguanodon. But we do think now that this Megalosaurus was both two-legged and four-legged. It could operate in both modes. And you'll see the changes to the body shape as we move up to 2001, which is where basically we've kind of fixed what we know about Megalosaurus. So you see how that's changed over the years. Even longer, 2019. Can walk on all four legs. Now let's move ahead to Sir Richard Owen. And in 1841, this is an extract of his paper, and we find in this paper, where the red circle is, the first naming of this group of creatures, Dinosauria. So it is due to Richard Owen that we owe that name. So we're getting there. How do we name them? If you were at one of my other talks, I had the Tree of Life, which is actually shown here too. We start at life, we work all the way down to species. The further down we get, the more specific we become about what the animal is. So, for example, we are a species. The genus is the whole group of humans. The family, it gets wider still. We name dinosaurs using the genus and the species. So Tyrannosaurus is the genus, Rex is the species. Sometimes we have more than one species in a genus, sometimes we don't. In which case we often drop the species name and we just talk about the genus name. T-Rex, we shorten it, that's Tyrannosaurus Rex. Sometimes a person gets honored naming a dinosaur. So in that other name, we see Knopfleri, that's named after Mark Knopfler from Dire Straits. His name got put into the name of that dinosaur, and that happens quite a few times. Right, a very busy slide. I wish I had more time to deal with this slide. I could spend quite a long time talking about this slide. Over on the right, we're looking at geological time from the beginning of the planet, all the way back to about 4.5 billion years ago. And on that, there's lots of information. We are not talking about most of that circle, because dinosaurs didn't evolve until much later. We are talking about the Paleozoic and the Mesozoic period up here. There's the Mesozoic, and right at the top there is present day. So most of this we're not talking about, as fascinating as it is. If we zoom in on the Mesozoic era, we have what I'm sure you've heard of, the Triassic, the Jurassic, and the Cretaceous. This is the period of the dinosaurs, and they lived all through this period. 140 odd million years. We've only been around for a couple 100,000 years, so they did really well compared to what we're doing. So that total length of time that they existed on the planet, I said about 140 million years. It started about 225 million years ago. A very important thing happened on the planet at that point. I'll get to that in just a second. And then they lasted up to about 65 million years ago, when something else very important happened on the planet. And we'll talk about that as well. You see here a time scale with some representative animals on that time scale as we're moving from 170 million years ago all the way up to the present time. And you see at one point all the dinosaurs have disappeared, and then we've got mammals at the top of that picture. What did Earth look like in those days? Not like what it looks like today. Let me go through a series of pictures showing you how the Earth looked like. So here we are 240 million years ago. And all of the land is sitting on tectonic plates. It is moving around on molten magma underneath in the core of the planet. Well, the core of the planet is solid, but as we come up, it becomes molten. On top of this, we've got our tectonic plates that are moving around. The continents sit on top of the tectonic plates, and they move. And so, 40 million years later, it looked a bit different. And of course, the light blue is shallower water compared to the dark blue, which is deeper water. And we move ahead to 150 million years ago. Some things are looking a bit familiar at this point. You can see South America joined to Africa in the middle there. And we move up 105 million years ago. You see they've separated. The Atlantic Ocean is beginning to be formed. And of course, these creatures are moving around, and they get separated slowly as these things move apart. One thing I want you to notice, in none of these pictures have you seen any ice caps. There wasn't any. In fact, and there we have it 65 million years ago, no ice. It was really quite warm, and that's the end of the period of the dinosaurs. And as these things moved apart, of course, it carried the different animals with it, and they evolved on the different places where they ended up. Right, extinctions. There's two very important extinctions on this. These are the mass extinctions. There's 5. We're in the 6th one now, we think, which is over on the far right. The one that's really important to us for the beginning of the dinosaurs is here, the Permian extinction, which is there. 96% of all species were wiped out. There wasn't much left after that. We got a barren planet. There's another extinction at the end of the Triassic. 80% of the species were wiped out. But then the most important one, as far as the dinosaurs are concerned, is number 5 up there, which is the end of the Cretaceous, 65 million years ago. And you can see we lost about 76% of the species. It was a little bit more selective. It wasn't a general extinction, but we'll talk about that towards the end of that. So that Permian extinction cleared the slate. And it was that clearing of the slate that let dinosaurs evolve. Let me talk about the Permian extinction a little bit more. It was due to, not us, we weren't here, it was due to volcanic eruptions, a lot of greenhouse gases being emitted up into the atmosphere, a lot of dust going up into the atmosphere, a lot of sulfur dioxide coming out of the interior of the planet. We had acid rain killing off vegetation. We had dust reducing sunlight coming into the planet, also killing off vegetation. It was a nasty place. Might have looked a bit like this. Who knows? An artist's representation of that period. And of course the animals at that point found it very difficult to survive and didn't. A lot of them did not. You might think Dimetrodon is a dinosaur. It actually existed about 40 million years before any dinosaur. It's what's known as a synapsid. It is a reptile-mammal crossover, or was leading to a reptile-mammal crossover, and this is, we think, one of the earliest ancestors that led to the rise of the mammals. But of course, Dimetrodon itself died out. A number of different species, about 20 species have been identified, and yes, it looks like a dinosaur, but it is not. It's a reptile-mammal crossover. About 20 of them were known, I think. Right, so let's look at an evolutionary tree. We're going to look at several evolutionary trees as we go forward to emphasize various things. So we've got the ancestral Archosauriform down at the bottom, the ancestor, if you like, of everything in that tree. It diverges over to the left, which is reptiles that we understand as of today, because we have crocodiles that exist today that come from that tree. On the other side, we have the Dinosauriforms, and from those evolved the dinosaurs and other things too. But I'll talk about the other things too a little bit later. So there's this big branch in the beginning where reptiles split off from the dinosaurs, even though they're part of the ancestral chain. We divided them into 2 groups. I always have trouble with these names. The Ornithischians. Yes, what a I don't know who comes up with these names. And then there's the Saurischans. And they did this based on the shape of the pelvis. So the Ornithischians, over on the right, they named those, and of course if you're familiar with that root, ornithology has birds, yes, but it has nothing to do with birds at all. No, it just happens to be the name. But the pelvis looks a bit like bird pelvises. No, nothing to do with birds. And then the other side we have the Saurischans. And from them, then we have several other groups that evolved from those, which you can see, and I'm going to talk about some representative animals from those groups as we go along. So that diversion happened somewhere around 240 million years ago, right at the beginning. The first dinosaurs that evolved, I've given you some names up here at the time that we sort of have located the fossils, and we've dated the fossils. And as you can see from the pictures of all of those 4 that I have mentioned up there, going back to as far as 243 million years ago, they were all small. The big ones come later. I'm sure you're all interested in the big ones, like the T-Rex. Well, we'll get to those. Now, this is a complete evolutionary tree of the dinosaurs with all the different groups. And you can see over on the left, we've got the time period running from 250 million years running all the way up to the present day. And you'll notice, with the exception of one part of that tree, they all stop in a dead line 65 million years ago. That is the Cretaceous extinction event. And there's one over on the left that continued. And we'll talk more about that again, but I might as well just pull the curtain back on this. Yes, birds evolved from dinosaurs. If you like, they still are dinosaurs. It's just they don't look like what you think a dinosaur looks like. But yes, they are from the dinosaurs. They come from the theropods. And the theropod included in its family Tyrannosaurus rex. So they're all related to Tyrannosaurus rex. And some of them still look like it. Okay. Dad, what was it like when you lived with the dinosaurs, Dad? My daughter used to tease me. Do your kids say that to you? Yes? Okay. Right, so over on the left we have obviously a human leading a dinosaur. Over on the right we have a University of Texas poll. And humans developed from earlier species. 51% disagree with that, so they don't believe in evolution. You can read the other figures. But the one on the right is the one that's really interesting. Humans and dinosaurs lived at the same time. 30% of Texans who were polled agreed with that. I hope none of you are from Texas. And 29% didn't know, and 41% disagreed. So 41% of Texans know that dinosaurs predated humans by a long way. Okay, moving on. How many? We are discovering new fossils all the time, actually, but since we've been discovering fossils and categorizing them, we have now got 300 genera. This is the larger group above species. Within that, we've identified about 900 species. Getting more all the time. These numbers are going to get bigger and bigger as time goes on. And some representative dinosaurs there you may recognize. Fossils. You might think a fossil is just a piece of stone that's been formed somehow. There are 8 different ways that you can make fossils. Some of them are molds of footprints. Others are changing of the minerals within, and I've listed all the ones there. And each one of these different fossil types can give us different information. You'll see the one in the center. That's a fossilized feather. So we see the structure of the feather. In some other fossils, we have information about the original content of the material, like eggshells. We also have information in certain cases about color. So we even know that some of the dinosaurs had some colors and we can detect what they are. The science is amazing in what we can do. There was a very interesting period in the United States that was known as the Bone Wars. These two gentlemen shown up in the top right. We have Marsh on the left of the two pictures, and we have Drinker on the right. Two wealthy men who were hunting for dinosaur fossils. The rich one won. So Marsh discovered 80. He was richer. Cope only discovered 56. And you can see the motley crew of diggers over on the right. This was really quite the competition, but nonetheless, out of the Bone Wars, a very famous dinosaur was discovered. It's shown here on the left, and that's Stegosaurus. I'm sure all of you have heard of Stegosaurus. So that was discovered in the Bone Wars, as were many others. How do you become a fossil? It's not as simple as you may think. Well, first of all, you've got to die. Yes, that's the first thing, die. Don't be too big or too small. Don't be too soft. It would be nice if you had some bony material within you, because that's the part that often fossilizes. Get buried quickly, very important. You need to be covered up quickly. Hopefully you get covered up before scavengers come in and rip your body apart. If you can die in a group, that's also better, because then the scavengers will perhaps concentrate on other creatures in the group. And of course, the most important thing is die in the right place at the right time. So you can imagine that not everything that lived gets fossilized. We're getting a very small portion of what lived during that period. I have to diverge slightly into geology and explain to you very briefly the rock cycle. There are basically three fundamental types of rocks. There's igneous rock, which comes from volcanic action, magma coming up from within the earth. That cools, it becomes rock. That's igneous rock. There's no fossils in igneous rock. Then there's metamorphic rock. This is rock that is taken from the surface of the earth through tectonic action and goes back into the body of the earth. It gets remelted or compressed or partially melted and compressed, and it changes its form. There's no fossils in that either. Any fossils in that would be destroyed. It is sedimentary rock that we find the fossils in. And sedimentary rock is formed by erosion on the other rocks, giving you dust. You can also have little skeletons that come down on top of you if you're in the water. It gets compressed, and the chemical action takes place, and you have fossilization. So only sedimentary rocks can we find fossils in. So I just said the first bullet, and I said the second bullet. And the map over on the right shows you the major dinosaur fossil sites around the world. And you see pretty much every place we found fossils, including Antarctica, which didn't used to be ice covered when they were living. Another tree, separating the Ornithischians from the Saurischia, and over on the left, some representative shapes of the dinosaurs that evolved, and you'll recognize some of those shapes. The picture up on the top left, again showing you some familiar shapes. And just for example, I'm sure you wanted to know what some of the big ones look like. Down at the bottom left, we've got one of the big ones. Comparison to a car and a comparison to a people. And these very large ones that you see there, like the Apatosaurus, used to be called Brontosaurus, but that's another story. They were all herbivores. They did not eat meat. It's the theropods that ate meat. So within the Saurischia, we have three major groups. I've listed their names up there with the translation of what that means. So the theropods, beastfoot, the prosauropoda before the lizard-footed, and the sauropoda, lizard-foot, and some representative pictures within those groups. Bipedal, 2 feet, hands for grasping. Sometimes they got really small, as in T-Rex. Specialization for feeding, teeth to break bones and tear flesh. And some of them, feathers. They were covered in feathers. Feathers evolved long before flight did. Feathers were used as a coloring for mating. Feathers were used to maybe keep the dinosaur warm and keep it dry. They were recovering, kind of like clothes. In the theropods, they could be giants, or large, much larger than us anyway, or they could be small. I've given you an example here of Sinosauropteryx, which is about human size, and it was covered with feathers. This is Gigantosaurus. This was the biggest that we've discovered of the meat-eating dinosaurs, of the theropods, and you can see up to almost 14 tons, and in the picture how big it was compared to a human being. Here's some more information about Gigantosaurus. They lived for a few million years. They weren't that successful. They were not contemporary with Tyrannosaurus rex, so any fight between Gigantosaurus and T-Rex in reality never would have taken place. Of course, in Jurassic World, they bred those dinosaurs different. Now, T-Rex is very interesting because of all of the animals that we have found so far and modeled, it had the strongest bite force of any animal that we know. It could crush 8,000 pounds worth of material. It had a bite force of over 35,000 newtons. Compare our bite force of 300 newtons. That's a measure of force. So 35,000, they could literally tear the top off a car that you saw in one of the movies. They could indeed do that. And up in the picture there, you see some representative theropods. A little animation of T-Rex, narrated by a very famous naturalist.
Hollow air-filled bones and powerful hind limbs make T-Rex very effective swimmers. This is an adult male. with his young family. T-Rex has the most powerful jaws in nature and can bite with the force of over 5 tons. The young are keen for a taste, but he's not sharing it. Tyrannosaurus Rex. North America's top predator. With his 6-inch long teeth, tearing through an alamosaur's tough skin is not a problem.
6-inch long teeth, about this much around, and serrated. There's a paper here that was published some time ago, and what they tried to do is estimate how many T-Rexes lived at any one time, and what the total number of T-Rexes were over the 2.5 billion years that they lived. And they got up to about 2.5 billion T-Rexes, but at any one time, somewhere in the region of plus or minus, within a factor of 10, 20,000. So within the Washington, D.C. area, you might run into 1 or 2. Not so bad, right? You could probably hide from that. They can run faster than you, though. These are the Prosauropoda. They were found in the late Triassic to early Jurassic. That's 229 million years to 176 million years ago. Weren't big. About my height, a little bit more than my height, so not big, and you can see some representatives there. Although, maybe not very tall, several tons in weight, so substantial amount of weight. These are the sauropods. These are the giants that you're familiar with, the big herbivores. Once thought that they could only live in water because they needed to support their body weight, but that's been proved not to be the case. The largest one is the Argentinosaurus. That could be up to about 35 meters long. And then I put the dimensions in feet too, and there's a little human down here in the bottom left in case you didn't see it in comparison to the different sauropods that we have identified so far. Now we go to the bird-hipped dinosaurs that have nothing to do with birds, the Ornithischia, and there are 5 major groups in there. The first one I've shown you a picture there, the Ankylosaurus, and we'll talk about all of those very briefly as I go through the 5 major groups of dinosaurs. So this is Ankylosaurus, which is really an interesting dinosaur because all over its body, it's got bony little plates. The lumps that you see on the outside, they are bone. It's even got little bony plates on its eyes, and at the end of the tail, there's a big club that it could swing around. And you see the size relative to a human there. Bony plates with a bony tail that it can swing as a mace. And it's about the right height to take out a T-Rex leg. So it could crush the leg. Kind of like a tortoise with its shell, very hard to get into. In this case, it could defend itself. Smack in the head, another smack in the head. And it's quite likely that Ankylosaurus could take out a T-Rex with this weapon that it had like that. Stegosaurus, of course, a very famous one. We've identified 3 species of Stegosaurus. Interestingly, the time difference between Stegosaurus and T-Rex is longer than the time period between us and T-Rex. So there was a big time difference between these 2 animals coexisted on the planet. So if you think of T-Rexes fighting Stegosauruses way back when, that never happened because they had died out by then. Does anybody remember this? I remember this. I was fascinated with dinosaurs as a kid, that some dinosaurs had 2 brains. Does anybody remember this? I see someone nodding there. Maybe he's falling asleep. No, I'm just kidding. No, I'm just kidding. And the reason is, Marsh here, when he dug up the Stegosaurus, he found this big cavity at the back of the Stegosaurus, above the hind legs, and postulated that because this animal was so big, and that the brain case at the front was so small, that it had two brains. It had one brain at the front for cognitive actions, and then one brain at the back to control the legs, as it were. This is not true. This is a myth, and that's no longer correct. We have another famous one that I'm sure you're all familiar with. This is Triceratops, a grazing animal. You can see its size compared to a human there. Obviously the horns are very defensive. The frill around the neck, not necessarily so, probably used for species identification and also as a display for mating. This is the Pachycephalosaurus, with reference to a human there. Now, on top of the head, right here, that's all solid bone. And they've actually found fossils where they've looked at that bony case and they found markings consistent with headbutting, as the mountain goats do. So it's believed that that bony surface on the head of the Pachycephalosaurus was for mating purposes and to decide who was the strongest one, so he got the female. These are some ornithopoda. I'm not going to say much about them, but just to show you the different animals, again, reference to a human being, and you see they go from really quite small up to quite large. They're color-coded. You see their proper names over in the right, all tongue twisters. These are the hadrosaurs. The hadrosaurs have this wonderful display on top of their head, which is actually hollow. And it's found to be connected to the airways, so we think, and in fact, when I play you the sounds, we're pretty sure that it was used either as communication calls or mating calls. And this is a reconstruction of what that bony protuberance on the head, which is hollow, would have sounded like. Right. Sea and air. There were no dinosaurs in the sea. You might think there were, but there weren't. They were all marine reptiles. There were no flying dinosaurs as such. When you think of the pterosaurs and the pterodons and Quetzalcoatlus, these are flying reptiles, and you see the size of a reconstructed Quetzalcoatlus next to a person there. Their wingspan would have been from one wall to the other. Gliders mostly. Not dinosaurs. These are the pterosaurs. You see what they look like. And in this picture there is some kind of covering on there. But remember, I said the feathers came before the flying. And it did indeed. The feathers came before the flying, but they were adapted as evolution went on. So, not dinosaurs. Pterosaurs are not dinosaurs. They are reptiles. These are the marine reptiles, Mosasaurus and Plesiosaurus, marine reptiles, not dinosaurs. And of course, the one over on the right, we think maybe is the Loch Ness Monster. Well, at least that's the theory. Nobody's ever found it yet. But there are some pictures that pretend to look like a Plesiosaurus. And then there's the Ichthyosaurus. This is the one that Mary Anning found. And we have a fossilized skeleton in the top right there, and that's what she found. She actually found complete skeletons, complete fossilized skeletons of dinosaurs when she was hunting for them in England, which is where she was based. Again, a marine reptile, not a dinosaur. Now, that being said, of course, there's always an exception. This is Spinosaurus. This actually is a dinosaur that may have had an aquatic life. If we look at Spinosaurus, we see that due to the air sacs within, I'll talk about air sacs in a minute, it was very buoyant. It could well have been mostly aquatic, but we're not 100% sure. So the jury's still out on whether there was really a swimming dinosaur or not. But this is the most likely candidate for it, which is Spinosaurus. So how do we know anything about what I just told you? Let me explain some of the things that we have found out in the past, and some of them quite recently. Extant phylogenetic bracket, developed in 1995. So how does this work? If we have existing creatures that have evolved from a common ancestor on one side, and we have existing creatures that have also evolved from a common ancestor on the other side, then the characteristics of these two living creatures that bracket the ones that went extinct are likely to be common across the board. So now, due to extant phylogenetic bracket, we think that dinosaurs did see in color, because crocodiles and birds do. And these bracket dinosaurs. Birds also see in the ultraviolet. Crocodiles do not. So we don't know whether dinosaurs could see in the ultraviolet. So that one, I don't think we will ever solve. But that is a very powerful technique in trying to determine characteristics of things that have been extinct, if we can follow it back to a common point. We can now do CT scanning on fossils. So for example, in heads of dinosaurs, we can look inside. This means we can figure out what the brain shape was, and similarly, using the previous technique I mentioned, we can get some information about what we think the brain did in a dinosaur. And we can even figure out how smart they were, but we'll get to that as I go along. Some other things that we know, finite element analysis, we can reconstruct the bite force. I've already talked to you about the bite force of T-Rex, the strongest known. We can use biomechanics. There's an example up there in the animation. We can figure out how they moved. We can look at the footprints in the ground, the fossilized footprints, and we can figure out how they moved. We also know information about the stress on their bones from the size of their bones. And then the geochemical analysis of some of the fossilized, we still got the original material in the fossils. That gives us information about all kinds of different things, including the body temperature of the animal at the time, and we'll be talking about that. All right, how smart were they? This is the encephalization quotient. It's a measure of intelligence, if you like. The quotient for dolphin and human up there is shown at 5.3 and 7.5 respectively. You see the different groups of dinosaurs there, with the sauropoda down at the bottom left, going all the way up to the non-avian theropoda, and I've included for comparison both the dog and the raven, so you can see roughly how good dinosaurs were. In other words, if we had some dinosaurs that corresponded to the dog encephalization quotient, we could, in theory, train them. Sit! T-Rex sits. Yes, eggs. They all laid eggs. Yes, they did. And we've even been able to reconstruct some of the eggs. We've even been able to reconstruct some of the colors of the eggs. And this chart shows you what some of the eggs look like. They had different strategies. Some of the dinosaurs would bury their eggs. Some of them would incubate their eggs. So they had different strategies for looking after their young. And we found evidence that indeed they did look after their young. Not like snakes necessarily, where they get born and off they go their own way. Breathing, very much like birds. Birds have air sacs in addition to their lungs. We found the same sort of cavities within dinosaurs, which of course leads to the evolution of birds from dinosaurs, because they've all got the same breathing mechanism. But yes, they had air sacs, so a different process. Very important question, of course. Once we all thought dinosaurs were just big reptiles, so they were cold-blooded. Well, how the hell did they live up in the Arctic and the Antarctic? Yes, there was no ice there yet, but nonetheless, there was no sunlight for half the year in those places. We've got lots of evidence to show that dinosaurs were not cold-blooded. They were somewhere in between. What we call them is mesotherms. Some were cold-blooded, some were warm-blooded, and the bulk of them was in this range, which we call mesotherm. Where you see black up there, these are the mesotherms. Mesotherms can somewhat regulate their body temperature, by their metabolic processes, as opposed to reptiles that need the external heat, and as opposed to us where we generate our own heat. So dinosaurs are basically in the middle there. Now we're getting near the end. This was a very bad day for dinosaurs. We had a large meteor strike on the Earth. It would change the Earth for several years, destroyed the food chain, destroyed the weather, and led to a whole bunch of fossils, which we are now detecting. After that meteorite strike, it's like a wall came down. Basically, nothing bigger than 25 kilos survived. This curtain came down and nothing bigger than that could get through it due to the changes on the Earth from that meteor strike. It's also thought that there were some other things going on at the same time, some more volcanic eruptions, because if we look at the fossil record, we see that dinosaurs were diminishing ahead of the meteorite strike. So this is like the cherry on top. Let's finish them off. Bang. And they were all gone. This opening led the way for mammals to evolve, and of course, when mammals evolved, it led to, finally, us. If it had not been for that asteroid strike, I don't know. I've already mentioned this. They're still with us. They don't look like it anymore, but all the birds you see have evolved from the theropods. And the theropods includes T-Rex. Now the birds came from the smaller theropod group, so they're not that closely related to T-Rex, but nonetheless, they are. On the bottom right there, we see a cassowary, and gosh, doesn't that look like something that might have been stalking the Earth 65 million years ago. One of the most dangerous birds on the planet, actually, with its claws on its feet. It can rip your intestines out. And that brings me to the end of the Age of Dinosaurs. Thank you very much. I will be doing science trivia today, and I will be back in here at 4 o'clock talking about coffee. I love coffee. I'll teach you how to pull the perfect shot if you want to pull the perfect shot. That's at 4 o'clock today in here.